So this is in the Engel and Reid, that third edition book. This is figure 26.1. And I'm asking you the question, if you were to look at this potential energy surface, now we call it a surface, but in this particular case, we're only showing one dimension of that surface. So we've got a complex shape that's a function of 3n variables. It really, the rotations and the translations are gone. So it's really 3n minus 6 molecular variables that we have in this energy surface. And we've taken a single cut through that, and the variable that we've chosen to cut through that potential energy surface is this torsion angle, the carbon-carbon bond torsion, or dihedral angle. And what we see here is so we look at that red curve, and we call that a potential energy surface. Okay? Everybody with me so far? Now, in your mind, you should be able to take that function and turn it into one of these classic systems, classic thermodynamic systems. And if you were to apply the Boltzmann distribution to it and figure out what the probabilities of populations are, that's something you can do by hand. We did it in class. What kind of system would that be? Do you know what I'm asking? So if we were to write out a problem and say, tell me the probabilities of being in the anti or gauche. So I hear probabilities, I think Boltzmann distribution. I think, with and without degeneracy. I'm thinking, how many energy levels am I talking here? So what kind of energy level system is this? And does it have degeneracy or not? So let's first talk about how many energy states are there?
3, 4, 4.
I've got 2, 3, 4.
Just 4. There's 4.
If you're only comparing gauche and
4. Okay, I've got up to 4 now. But that's good. At least we're at 4 and not infinite. Okay. Can we eliminate some of those? First of all, someone tell me what one of the 4s are. The ground state. Okay, what's the next one? Here, these guys. Okay.
Next is the
These guys here, and then the very top one. Are these tops of the hills ones that we need to consider in terms of our probabilities?
Yeah.
Why do you say we need to consider them?
I mean, we've never not considered them, I guess. We had problems where we considered high energy states and low energy states.
Okay.
So,
But are you going to find a molecule there?
there'd be a small
In terms of
percentage.
it's be what?
I think it's a small percentage.
Very small percentage.
So
Yeah.
you can consider.
So it'd be so small you probably couldn't detect it. So we have a really difficult time detecting molecules that are in transition states. They're almost impossible to find. Yeah. So the tops of these hills are transition states between minima. And so that eliminates the tops of the hills. Okay? So that's why I want to really focus in on this picture, because you can look at this and you say it's a 2-level system with degeneracy in the upper level. This is a singly degenerate ground state and the doubly degenerate excited state. And so it's a 2-level system with degeneracy in the upper level. And you could do that by hand. And we did that in class. We did that example. So here's a real life example of a 2-level system with degeneracy. And you don't need to consider the transition states. Now, sometimes we do use the Boltzmann distribution to figure out how probable it is a molecule can get over the barrier. And that's a kinetics calculation. It's the Arrhenius equation. That's the activation energy. So if I dump all of the molecules into, see if I can use the pen. If I dump all of the molecules into this level, I could use this distance from here to there as the activation energy. And if you look at the Arrhenius equation, it's e to the minus activation energy over kT. That's the Boltzmann distribution. So the Arrhenius equation is the Boltzmann distribution. The Planck equation uses the Boltzmann distribution. So you see why I'm so big on Boltzmann. All these other people have their names on equations. They're all using his math. Not bad. Okay. And so if you want to figure out what's the likelihood, what's the probability of a molecule that's been dumped into this level of overcoming this barrier to get down here, then you can use the Arrhenius equation and use this energy difference as the activation energy. So molecules are going to go down here. What do they have to do to get back? To get back, they've got to overcome 16 kilojoules per mole, whereas earlier we only had probably 14 kilojoules per mole. So more molecules are going to go in the forward direction than in the reverse at first. But eventually you're going to have so many molecules down here that a few of them are going to come back. And there's going to be so few left here that only a few of them go forward, and eventually those rates will equal each other based on the relative populations. And so it will look like the populations are static, but there are molecules going both directions at that temperature. And the faster rate in the reverse reaction is because there are more molecules in the lower state to make it over that hill. And the slower rate in the forward direction is because of the smaller number of molecules that are still in that excited state. And so you will establish equilibrium, but it's what we call a steady state. There's still change going on, but you don't observe the change. And it would be very difficult to detect the few molecules that are going over the top. So we don't use those in our equilibrium calculations. We just use the minima as our equilibrium calculations. So that's using a potential energy surface. And I tried to explain why we use the word surface when we're really just taking a slice through that surface. Then we talk about looking at the potential energy with respect to the different coordinates. The second derivative of that will tell us the curvature. So the first derivative is the slope. And if you're in the minimum, the slope is 0. If you're in a maximum, the slope is 0. So that tells you where the critical points are in terms of mathematical critical points. But then the second derivative will tell us if you're at a minimum or at a maximum, because the curvature is either going down or going up. So the slopes are changing, either getting down or going down or up. So up here, this second derivative with respect to the coordinate up here is going to be negative because the curvature is down. As I increase the reaction coordinate, notice the slope is decreasing. So it's curving down. Whereas down here, if I increase the coordinate, the slope is increasing. And so if the second derivative is positive, you're at a minimum. If the second derivative is negative, you're at a maximum. And the square root of that second derivative is the force constant. Okay? And so the square root of a negative number is imaginary. And that's where the imaginary frequencies come from. So if you're at a maximum and you figure out the vibrational frequency, it's going to be a negative number. So that's why we have those negative vibrational frequencies. This matrix of second derivatives is called the Hessian. That's one of your vocabulary words, and essentially it's just defined as this diagonal matrix of the forces in the molecule. The second derivative of the potential energy surface with respect to the various vibrational coordinates. There's quite a lot about, I kind of went through this in my PowerPoint. So this Hartree-Fock molecular orbital theory, they actually simplify it even further, and they say, look, we've got the nuclei components, but they're constant, so we drop those out and just have the electronic Hamiltonian. Homolytic bond cleavage, I put that in as a vocabulary word, just because I want you to make sure that you realize what's going on with homolytic bond cleavage. The electrons are unpairing and being pulled out with each of the species. What does that do? This is one of the major points of this reading, is that when you have a pair of electrons and you separate them, notice that pair of electrons was being either neglected or explicitly calculated in terms of electron correlation. But when you separate them, they're no longer paired. And so that electron correlation term is very different for the products versus the reactants. And so whenever you do homolytic bond cleavage, that's the worst possible case for this electron correlation errors. Okay, and you can see that throughout the tables. Whenever we had homolytic bond cleavage, the errors in bond energies were horrific because of that electron correlation term. You know, the products have unpaired electrons and the reactants don't. So if you want to actually compare species, what you really ought to do, instead of trying to break a bond, you want to compare it to bonds that you're familiar with. And so you have molecule A bonded to molecule B as reactants, and then you have A's bonded to A's and B's bonded to B's as products, and then you've just changed the types of bonds, and you can tease out the relative bond strengths. And if you know the bond strengths of A and B together, then you can figure out the bond strength of A to B. And that's what they're doing with some of the proton affinity calculations and things. Notice they don't have just a proton being pulled off the molecule. They have a competition for that proton between two bases. And so there's some computational strategies in here that I want you to think about when you're coming up with your project. So a lot of the calculations done in this chapter may be very useful for you in terms of coming up with your project and how you might want to approach making this computation relevant to your research. Let's see if I highlighted some things in here. Okay, let me back up. Here, down here is a mention of the kinetics piece in the Arrhenius equation. So, and so you have this rate constant is equal to some frequency factor in front, and the frequency factor is just a measure of how likely that reaction is. If the energetics are fine, you know, these molecules have enough energy to collide, but do they have to be oriented just so? All right? If there's really no orientation effect, then A will be big. But if there's a really particular orientation effect, think like an SN2 reaction, which got to come in from the back side, then that kinetically is going to be disfavored. Because if it hits it on the side, it has enough energy to react, but it hit it in the wrong place. And so that frequency factor will be low for an SN2, but it might be high for just two hydrogens finding each other and making H2, right? It doesn't matter what direction the atoms approach each other. And so that would be a high prefactor for just hydrogens reacting with each other. And so it's really difficult to find out from first principles what that A factor would be. You have to do experiments to get the A factor. So in one of the options for the project is to do a transition state and to calculate the Arrhenius-Reid equation. In that case, you would just say, assuming A equals 1. So since you don't really have a way to make A different than 1, you would just write in there, I'm assuming that the prefactor is 1. If we find that the prefactor is much less than 1, then my rate constant will just be reduced linearly. So it's really not a problem to tell them, I'm just, for A equals 1, this is my rate constant. What you will find, though, is the energy of your reactant and the energy of the transition state. You take the difference in those energies, and that would be the activation energy. Compare it to the temperature. This is Boltzmann's constant. So this is the Arrhenius equation, and allows you to get the rate constant. So I don't know if that's a calculation that you'd want to do. That's one of the options, though, is to find a transition state for your system. The text, I want to just sort of point this out, that they talk about the Hartree-Fock limit, where you've taken the basis set all the way up to sort of infinite number of basis functions, which you can't do practically because you don't have an infinitely sized computer. And so you have to define what the Hartree-Fock limit is, and they define it. So I want to make sure that you caught that in the text. That's on page 639, and it's right here. So he's saying it's important to realize the calculations can't actually be carried out at the Hartree-Fock limit. So they just picked a really big basis set and said this is going to represent the Hartree-Fock limit, and then we can compare all the other calculations to that calculation. And so this is an important assumption for all of the sections that follow and all of the tables that follow. They have here that it's this particular basis set they've designated as the Hartree-Fock limit for this particular chapter. Okay, that's not a universal definition. That's this person's definition of what the Hartree-Fock limit is for their tables and their comparisons. But that was an important thing to point out, and I'm just trying to point these things out to you because you're reading the chapter too, and you might miss some of these really important pieces. And so that's a very important paragraph. Because if you're going to compare things to the limiting case, sort of the infinite basis set, and you think about that, wait, how did they do the infinite basis set calculation? They've told you right here in this paragraph what they consider the infinite basis set for their calculations. That also gives us a good insight into what is considered a big basis set. So it just has diffuse functions on the big atoms, and he has 2 stars on there, which that's the old terminology. Now we put parentheses and explicitly say d orbitals on all the heavy atoms and p orbitals on hydrogens. And now that's one of the vocabulary words. What is a heavy atom in terms of computational chemistry? Did you see that vocabulary word in the list? Do you know the answer?
Bigger than hydrogen.
Pardon?
Bigger than hydrogen.
Anything bigger than hydrogen is a heavy atom. So this was definitely written by physicists. Have you seen the physicist periodic table? And then you got a bunch of little things around the outside. So that's the physicist periodic table. Okay. And so everything else is a heavy atom, and then hydrogen. That's the light atom. Okay. So that's the way we work in Gaussian as well. So when we have the single star, you'll see G star. That first star is talking about the heavy atoms and putting polarization functions on the heavy atoms, and then the second star would be hydrogen. Now I like it better. They put parentheses and put a D, comma, P, and that's D orbitals. Now you could do more. You could do D and F. So you could put D orbitals and F orbitals on the heavy atoms. And you could put P and D on the hydrogens if you wanted to be crazy and give your hydrogens access to D orbitals. Okay. I don't know why a hydrogen would want that, but it's okay. It's going to just make your calculation longer, and it might lower your energy by, something in the 4th decimal place. Okay. So it's going to use, maybe 1,000th of that D orbital to give its electrons a little bit more freedom. But if it doesn't need it, it won't use it. But it'll still calculate it, which means it'll take your calculation longer to finish. So I don't really recommend it. Adding things that aren't necessary really just wastes a lot of time. Let's go back. Oh, here's another big word that just kind of flies by. It says Hartree-Fock models are variational. That's a big phrase right there. Now, who of you would have known, oh, that's important? Probably nobody. This is what is meant by variational theory, okay? Because we have limited the electron in their orbits, okay, and because we're neglecting electron correlation, we have this situation. Energy of the Hartree-Fock model will always be greater, or we'll go ahead and let the hopeful case of it being equal to, but it's never equal, the exact energy. So of the real molecule. So that's the sort of the variational theorem. So the ramifications of that are lower energies are more accurate. That's a really useful conclusion, don't you think? Because you've got to know if you're getting close to the answer or not. And so if you're moving your electrons around and they're picking different orbitals and they're including some d orbitals and so on, if that lowers the energy, it's getting closer to the exact energy of the real molecule. Okay, this is our compass. This is telling us if our calculation is on the right track. Did it lower the energy of the molecule? Yes, then we're getting closer to the right answer. Okay. Yeah, and that's what, so this variational theorem, that word may not mean much to you, but now it does. You're like, okay, and then they'll say, but they'll say DFT methods are not variational. You're like, uh-oh, what's going on? Or this method's not variational, which means you've got a problem with your compass. Okay, they've done some things to kind of correct for that to make sure that they can get back to this variational principle, but HF methods definitely are variational. So if you can get a lower energy with the HF method, you're getting closer to the right answer. Okay. What's that?
It's a lot of ECFT.
Well, yeah, I mean, yeah. So hopefully this is useful when, I mean, you're reading this, I'm reading this, and I'm pointing out the things that are really important so that you might have gone past. I talked about homolytic bond cleavage being prone to errors. There's a mistake in table 26.6. Up here, this really confused me. Up here it says structures of one heavy atom hydrides. Okay, and I'm looking at this. And then the next one says bond distances in two heavy metal hydrides. And I'm like, I don't see any metals in there at all. Okay, so I think that just you know, typing wise, they're like heavy metal. It just goes together, either in music or in, you know, toxicity. So, you know, it just goes together, right? So I think that was just a typo. So you scratch through that metal part. This is heavy atom. You know, change that to heavy atom hydrides. Yeah, there's no hydride on the difluoride, so yeah, that seems strange, but I guess I threw it in there for comparison's sake. But yeah, so that's heavy atoms, and that also made me think, okay, probably I should put that in the definitions list as heavy atom versus light atom because they're using it in the table, and you're looking at this going, heavy metal, that doesn't make any sense. Yeah, there's no metals there, so I didn't want you to make the conclusion that every other element is a metal. Like nitrogen's not a metal, okay? So I can mark through that metal part. Fluorine's not a metal either. So it just means heavy atom. So that's why I changed books. No. So, I used to use this book. It's a good book. Just for the tape, it's a good book. Some more about electrolytic, or yeah, there's a shout out to John Popel on 643, so that's great. For years, Popel was my password on my computer because of John Popel. Yeah, it's not anymore. Yeah, so but that was so cool. It was like he's the king, you know. 1998 Nobel Prize for bringing computational chemistry to the masses. I was in the masses. That's right, yeah, he came up with all those, I'm sure. And then Cohn here on 647, they point out that he won the Nobel Prize for the DFT calculations. That's pretty slick. Okay. There's a little bit about the Gaussian basis sets in section 26.7, where it talks about the Slater type orbital, and it shows the the wave function. So let's go there. So down here at the bottom, oops. This is a Slater type orbital. That's a whole lot of stuff. Let's see if we can find some important things in here. What do we see? First of all, we see it's a wave function. It's a three-dimensional wave function. R, theta, and phi. So spherical polar coordinates. This would be a hydrogenic wave function. Okay. We've got all of this stuff out front. I'll go ahead and tell you all this stuff in front, those are all constants. Here's a quantum number, again, that's the principal quantum number. Okay. So, and here's the principal quantum number, but there's a bunch of constants. Those are going to serve as the normalization constant for the wave function. Okay. Then we have, again, a piece that's part of the radial wave function. The e to the minus r over a naught, that's the radial wave function. And then this piece, YLM, do you remember what that's termed, what that's called? We call, it has to do with angular momentum. So L is the angular momentum quantum number, okay. M is the magnetic spin quantum number, or the orbital spin quantum number. But what is this Y of theta phi called? It's a set of functions.
We split into half. We put hydrogen into the radial.
Yeah, there was the radial part and the angular part, but that angular part, they just grabbed this set of functions because they knew that it would satisfy a eigenvalue eigenvector equation, like the Schrodinger equation. So they knew that this set of functions would satisfy that second derivative eigenvalue function, and so they just grabbed them. And they knew because hydrogen, it's an atom, so it's probably spherical, and so that they knew this set of functions would describe a sphere. What do you say, Will?
It's not related to psi, is it?
Well, this whole thing is psi, but we call it phi. I mean, for some reason, it's labeled with phi instead of psi. So you could just as well put a phi right here. Yeah. But this has a particular name, and it's called the spherical harmonics. Spherical harmonics functions. And that's where we get the S, P, D, F, G, H, I, it keeps going, okay? That's the angular momentum parts. And that's unchanged in Gaussian. We still use the spherical harmonics in the Gaussian software as those polarization functions. It's this piece, e to the minus r, that's changed. It's the radial piece that we would like to get away from. We can solve this equation exactly for the hydrogen atom, but if you get to multiple electrons and so on, we have to do it numerically. And the computational cost of doing this numerically is too costly. So it takes too long to compute when compared to a Gaussian function which has analytical integrals. So let's go to the next page. There it is.
The integrated flashbacks.
Yeah, yeah, yeah. So they've just shown you the radial piece because the angular piece is the same. So just the radial wave function has been changed, and now you have e to the minus r squared. So that's the piece that's the Gaussian piece. Okay. And I showed you this in the notes, but here's a picture of the two. Yeah, the red one is the Slater type orbital, e to the minus r, and the blue is the Gaussian. And so they're not exactly the same, and in fact they're dramatically bad right here. Because what's going on at 2 angstroms where this fails to match? That's the bond lengths. So where we need these functions to be good, they're bad. At the nucleus, they're bad too, but there's not a whole lot happening at the nucleus. So if we can just fix this problem out here, then we'll be better, okay? And so that's why we have all of these contracted Gaussians. So this is 3 Gaussians combined to give us this blue curve, and you see now it matches this hydrogenic function in the range of 1 to 5 angstroms. That's where the action is, where the atoms are close to each other. So we have corrected these radial distribution wave functions so that they're accurate in the 1, 2, and 3 angstrom range. That's really important. Now, what about radial nodes? You know, if you go from the 1s to the 2s, there's a radial node. And to the 3s, there's 2 radial nodes. And the 4s has 3 radial nodes. Well, that's just going to be a polynomial multiplied by this function. So if I get this function right, and I multiply by a polynomial, it'll go through the nodes right too. So if it falls off correctly, that's fine. I add a polynomial to it, it's still going to be fine. So that's okay. Eventually, though, it gets a little bit less accurate out here, and so then we have this minimal basis set and then the split basis sets. So the split basis sets only split the valence band, and so this is what's going on with the split valences. So for something like carbon, these are the functions, the different radial distribution functions we have. So every one of those orbitals has its own radial distribution function. So the 1s is a core electron in carbon, and so it just has 3 Gaussians dedicated to the 1s radial distribution function. And then the 2s and the 2p and the different 2p's, there's 3 of them, they have an inner Gaussian correction and an outer Gaussian correction. So it's split. Okay. So that's what's going on with this. The 1s and then the 2si, 2px, 2py, 2pzi, those i's stand for inner, and the o's here stand for outer. And so it's just taking the valence electrons and split them into inner and outer, and that helps correct, again, for that important bonding region. The valence band does all of your bonding. And you say, we're almost doubling the number of functions that we have to account for in Gaussian, but they have analytical integrals. So doubling the Gaussians and doing the analytical integrals really only doubles your equation. Sticking with Slater type orbitals, you have to iterate through, and the numerical iterations take way longer than this. So it's still faster. That's the bottom line. Okay? So that's how Gaussian's going on, and that's what this chapter is talking about in this particular section, is what's going on with split basis sets. Hello. Yeah, I know. Okay, there we go. Then it gets into some practical stuff. How do you select a theoretical model? Let's see if there's anything that jumped out at me. Yeah, I'll just point out, choosing a theoretical model is difficult because there are too many choices, and that's sort of pointed out over here. It's like it's not trying to find a calculation to do. It's like, which one do I do? You have so many choices that's a problem. And so what they did in the text is helpful to us because they narrowed it down to a small basis set, this 321G, a larger basis set, 631G star. So that's sort of what I call the industry standard basis set. They did different. They did density functional theory, and this again is the level of theory that I like to use. Is this B3OIP 6-31G with the d orbitals on the heavy atoms? Yes, Will?
I was like Googling stuff, and I thought the CCSD was like the gold standard for calculations.
Well, gold standard is different than industry standard. So gold standard is like the best. Industry standard is the run of the mill. It's like, yeah.
Cost over efficiency.
Yeah, you know, Kleenex will get the job done, but puffs with aloe, that's the gold standard, you know? Right. But it's expensive too. So, yeah. So that's, and then the MP2, which again is definitely variational. It's got an added perturbation theory on it with a large basis set. That's added in there as a check sort of on the B3LYP. But look at what the reason we like B3LYP, the density functional, is shown down here. This is the computational cost of those models shown. So if 1 is the Hartree-Fock with 6-31G, 1.5 is density functional theory, and 10 is MP2. So the MP2 calculation takes 10 times longer with the same basis functions as the HF calculation. Okay? And so that's what we would call a costly upgrade, right? You know, I would never buy puffs with aloe if it costs 10 times what Kleenex costs. You can get a box of Kleenex for 98 cents. We're talking about $9.80 for the gold standard. Probably not going to do that but once, you know. I got to try it out. Right? And so you might try out the MP2 on a small molecule and compare it to a regular molecule, you know. Like if you have a small case for yours, like in your bonding region in one of these borane molecules, if you get rid of all the rings and everything, you might be able to do a small example at MP2 just to see if the energy really drops and compare it to B3OIP and say, hey, they got almost the same energy, less than 10% different. That gives me permission to go with B3OIP, right? If they're 50% different, then you got a problem maybe with the B3OIP, right? Yeah, so sometimes you want to go ahead and do that just to test it out, or try the CC complete basis set, it's gold standard, but those are going to be really costly, so you're going to have to scale back your molecule. Yeah.
I haven't seen this part yet, but let's discuss, I guess, the issues with having mixed heavy atoms, like heavy atoms like iron with...
No, so the inorganics really aren't addressed in this chapter. Yeah, and so they can pose problems because they're so flexible in terms of where the electrons can be. Yeah. Okay. But I just wanted to point out that your computational cost for the MP2 can be, you know, up to 10 times more. And so that's a vocabulary word I put in there. What I mean by cost, you know, well, cost. When we talk about computational cost, we're talking about CPU time at the bottom of the calculation. When you finish, you have a 5-minute calculation versus 5 days. Time is money. So if you have to wait for 5 days and you get something that's really not useful, you really wasted a lot of time. That's a whole week. You only have 50 of those a year, you know, not counting, you know, 2 vacation weeks. so you've got, you know, you've wasted 1/50th of a year on something that wasn't worth it.
Even if it is useful, if you can get the same result through less intense calculation.
So it's really important to choose an appropriate model chemistry. The other type of cost is real cost, like that computer that Dr. Haynes just bought. That's costly, you know. What was the graphics card on that cost?
I don't know the price of that just that alone, but it's got a thing is $25,000.
The whole thing, that computer was $25,000. Yeah. So that's also cost. But most of the time when we talk about cost of a method, we're talking about the time it takes. But eventually it comes in. If your calculations are taking too long, you're going to have to go spend real dollars in buying a heavier machine. Okay. These calculations, when I talk in your paper, and we will on Monday. So over the weekend, look at this document. There's 3 types of projects. So let me flip to that. One option is to do a thermodynamic landscape. So that would be picking, say, a couple of different reactions. So that'd be 4 molecules, or if you have a single reaction of 2 species reacting and producing 2 products, again, you got 4 optimizations, 4 frequency calculations, calculating the energy of the products, energy of the reactants, delta G, delta H. So that's what I call the thermodynamic landscape for this reaction. That's option A. And now I'm not going to just let you dive into your research if you haven't demonstrated that you could do it for a known molecule. Okay, so like some of these competitive proton affinity calculations that are in this chapter, if you can do a couple of those, so 4 calculations on knowns, and then do your research would be the 4 unknowns. That's what I'm talking about here. It says 8 total optimization and frequency calculations, 4 knowns, 4 unknowns. So the 4 knowns would be trying to find if you can get close to one of the answers in the tables. So you're like, yeah, here's the answer I'm aiming for. I did my calculations. I got the same answer. Good, I know what I'm doing. Now I go do my research. If you don't know how to repeat calculations that are in the literature, you'll never know if you're right or not. And so isn't that what we did this summer? You know, we'll spend all summer just doing calculations that had already been done in the literature. But that's how he taught himself Gaussian. And then he can apply it to unknowns. So that's the thermodynamic landscape. The other one is the transition state search. So if you have a particular reaction that you're like, okay, this is so important to my research, I want to know what that transition state is. That's a real tricky calculation because some of these transition states are hard to locate. And so there you'd have to do a couple of known transition states and then do your unknown. But that one's a little more risky. And then this other approved Gaussian technique, if you'll just make the case to me that you want to do something else, this would be for someone, say, like who's already doing calculations in their research. Like you wanted to do molecular mechanics or something like that. Yeah, so, you know, but I want you to sort of get my approval before you chose that as a topic, okay? So that's the main point, is to pick one of those, A or B or C, if you're going to make the case for it. And then I put down here, the project report will have all these features in it, and then the rubric is on the back. So it's telling you exactly what I'm looking for. So by Monday night, we're just doing the top 3 rows in the rubric. Okay. And so you're not having to do the whole project, but just the top 3 rows. And I want to go ahead and see you demonstrate fluency in the vocabulary words. And so I'm counting the vocabulary words that you use in your paper. And I want for Monday nights, just at least 5 of those words used correctly in describing your project. Should be pretty easy, okay? Pardon? There'll be a Blackboard assignment that you respond to, and then upload your paper, okay? And then you'll get those things back as you work on your project, and you can revise that section, and that's revision points on the final project. So if there's misspellings, or if maybe some of your words were used in a clunky way, or not really necessary, you probably don't need to use variational theorem in your, because that's really not. So again, don't force it in there. You should probably have to use 5 of those words just to describe your project, right? And so that's it's going to be pretty easy. But Monday we'll talk more about the project. So look at this document, think about your research, look at this chapter, try to figure out, if some of these reactions that are talked about in the chapter, either bond cleavage or proton affinities or things like that, bond lengths, vibrational frequencies, if those spur thinking about your research, then we will look at those projects that you'd come up with.
Can you explain to me one time what's expected for the project idea statement?
Yeah, it's right here in the rubric. So find a rubric. Over here it says, technique A, B, or C are clearly chosen and described, and known cases are identified. So I'm going to do these 2 known cases, and I'm going to do my unknown molecule. The project relevance, I don't want you to go on and on like 20 paragraphs on your research. I'm limiting you to 3 to 4 paragraphs. And so it's got to be lean. This is what my research is, paragraph 1. This is how calculations may apply. This is the calculation I've chosen. This is the molecule I'm going to calculate. That's your project relevance in 4 paragraphs. So if you go too long, I take off. If you don't conclude enough, I take off. So look at this rubric. It tells you exactly how I'm going to grade the project. Okay. All right. This should be probably one of the most clear assignments that you'll ever do, because I took that teaching course last year, and they basically taught me how to make these kinds of clear instructions. So if there are any questions, email me, but study this document carefully because it's almost all of it is in there.